Yeah, okay, we're live now.
Oh, okay. Now we're streaming.
All right. Thank you again. So now we'll go a little bit more technical, I guess. So, oh, sorry, I think I got a. Give me a second. Right. So I think I have a mail about the presentation. Okay, I've just been informed that on the YouTube they think the same link doesn't work anymore, but I think it should work, right?
Yeah, I think now it's resuming. Yes, it should work.
Okay, it must have.
Maybe not the same link, but the same channel.
Same channel, yeah.
Because we stopped the transmission, so it may started another live.
Okay, let me message back. All right, so yeah, let's keep going. So now we'll go a bit more technical, let's say, and let's discuss this in detail. So I'll restart with the forgiving tree. So the forgiving tree, like I said, is the PODC 2008 paper. Also, I've had my tea now. I think I'm more active. I'm awake at least. So now the forgiving tree model, like I said, it's basically nodes are going to be deleted in some order, and you are going to do a P2P congest and self-healing model. So the same thing's happening now, except that every repair happens on node deletion. In fact, the order of the repairs need not be synchronous, so it can be asynchronous. So that's the good thing. What are we achieving? Graph is always staying connected. Diameter increases by less than or equal to log d, where d is the maximum degree of a node, and degree increases at most plus 3. Each repair is happening in constant time, constant distributed time, and involves only order d neighboring nodes. Okay, and there's a lower bound. So like I said, basically what you can do is whatever graph you begin with, you can just first make a spanning tree out of it and make it a rooted spanning tree, so that you have a parent on the top, and it's like a parent-child connectivity which happens. And the two operations which you do are the main operation being you replace the deleted node by a balanced binary tree of these virtual nodes, which we said is the nodes we're going to create, and you will short circuit out redundant virtual nodes as the number of real nodes keep decreasing, right? Because remember, the adversary can only delete nodes, and over time the adversary may end up removing a lot of nodes. And when you have a leaf node being deleted, it doesn't have any children, so instead of creating new virtual nodes, at that point you'll delete extra virtual nodes. All right. So in one sense, one can think, if an internal node is deleted, you add virtual nodes. If a leaf node is deleted, you remove virtual nodes, and that's how you end up doing some accounting in some sense. And now that accounting is quite important, which you'll hopefully understand by both this and the other algorithm. So firstly, we just to give an idea that this virtual graph approach can be quite useful. And how does it work? If you look at this diagram, this is sort of the idea. You have a real graph below, which is the graph you're trying to maintain whatever you like. And then you are creating this virtual graph, which can be a combination of these real vertices plus these virtual vertices, these new ones which we created. Right? Now think of these new virtual vertices. They are not really existing there, but where are they existing? So they are actually existing just in the memory of the real node. So imagine if I am a real node A and I create a virtual node A. What does that mean? That basically means I am creating this in my memory, which you can say is A dash, and then there may be communication or messages which come to A dash, but then these are being still simulated by me. So I'm simulating another extra node, but that idea is now this real network looks like a tree, whereas the virtual network looks like a tree, and I always maintain it like a tree. So now imagine that you have a real graph and then you create a virtual graph like this above that. And what you want to do, like we said, I say here method, is you want to set up this virtual graph on this real graph and then you maintain the virtual graph. You don't really think about the real graph. And supposing you have some property A which you want to maintain. Now what you can do is you can maintain this property A on the virtual graph. You don't need to really bother about the real graph, because sometimes like certain topologies like this tree is much more intuitive to think about and maintain. So you are maintaining this in a virtual space. Now this works. Why? Because there is a mapping between the virtual graph and the real graph. So as long as I have a mapping, for example, there are certain properties I want to maintain. Of course, I want to maintain them on the real graph. But what I know is if I maintain them on the virtual graph, then I have a mapping which guarantees me the same properties on the real graph. So for example, if I want to guarantee that my degree increase is +3 and I can do +3 on the virtual graph, and my mapping says that the degree increase in the real graph is not more than the degree increase on the virtual graph, and I'm done, right? And I'm fine. So this kind of idea makes this sort of virtual approach quite useful. So it can be, gives us useful for certain problem solutions, good accounting structure, easier to analyze and easier to visualize many times because you can create. So if you think about it, this virtual graph, you are creating your own vertices, your own virtual vertices. So you can create any sort of useful topology which makes it easier for you to think about it, right? That's sort of the idea. Okay, now how does it work here? You can see the way we created these virtual vertices, their nodes, they were always like on a binary tree, on a balanced binary tree, right? Now, the maximum degree you can get for a node on a balanced binary tree is 3, right? When the node is an internal node of a balanced binary tree. Basically that's the idea. So what you do is you create a virtual node with degree 3, and what we're going to do is we're going to make sure that each real node simulates at most one virtual node per real node. And then if you, of course, like I said, if you lose a leaf, then it's fine because you're just going to remove nodes. And this way you can always have, each real node will simulate at most one virtual node. So that is our idea. So the whole idea why we can sort of maintain this guarantee is by making sure, by creating an invariant that each real node simulate at most one virtual node. Now what does that mean? Since the degree of a virtual node is at most +3, and if you can guarantee that a real node simulates at most one virtual node, that means the real degree increase is at most +3. That's the whole idea of getting the degree increase. Okay. What about the distances? Now again, I'll give you a high level intuition. So what happens with the distances? Somehow whenever we remove a node and we replace it by a balanced binary tree. Now if this balanced binary tree is only consisting of the neighbors of that deleted node, and somehow we always maintain this property that you can never get more than those number of nodes in the neighborhood. Now you can imagine if this is a diameter path, every node on the way is blown up, but it's replaced by a balanced binary tree consisting of its neighbors. Now the maximum distance increase in this, you had one node and you blew up, this node blew up, so you had this path of say length 2. Now it's been instead being replaced by a ball. Now the maximum path in this ball is at most log d, right? At most the distance is at most log of the total number of nodes. So now this can happen over, basically all the nodes on the way. Then the maximum multiplicative distance increases log t. Right? So that's sort of the whole idea. Not going into detail how you get this. Now let us look at this in action, and hopefully this makes it more clear. Now node V is deleted. So see that node V has a parent P, and it has siblings I, J, K, and it has these children A, B, C, D, E, F, G, H, and H has children M and O. Now when this is deleted, then you get with A, B, C, D, E, F, G, H, and A, B, C, D, E, F, G, H, E, F, G in the center, and this node H, which we call air. Maybe I'll skip the technical reason at the moment why we keep this guy here, but we'll probably come to it soon. Okay, so now you can see that node V has been replaced by a balanced binary tree of its children, right? Each node being simulated. Okay, that's clear to everybody. Now let's try another thing. Now P is deleted. Okay, so remember the situation here. V is deleted and it has this A, B, C, D, E, F, G virtual nodes, and you have an H here because remember each of the nodes, each of the children can simulate one virtual node, so they put all of those in here. Now you have 7 virtual nodes as the balanced binary tree, 8 leaves, so you have one spare, right? This spare is very important actually, and this spare we call as the air. So node V had an air H, which is a spare, and it's kept here. Now when P is deleted, its parent, the adversary goes and deletes P. Now what will happen? P will be replaced by its children I, J, K, but also by H. Okay, because it already lost its child. Its child was V. So P has already lost its child V, so it must have some replacement, right? Now that replacement is given by this node H, and that replacement is this H. So you see now that it had 4 children before, it still has 4 children. Somehow this virtual child has come in. So you can do the same thing as before. Now you have I, J, K real vertices, real nodes, and H is a real node, but it's a one level down. It's another level here, but it's still a real node, but it is simulating this virtual node H here, right? So it is exactly this, almost exactly the same thing, except that the real node is now maybe 2 levels below, but you still can replace P by I, H, J virtual nodes and K as the extra air here, right? And now you have R. See, so now we have been able to grow the tree in this manner. Now similarly, when D is deleted, so now here D will go. D is a leaf node. So D goes, right, which means we will do the leaf deletion, which means we'll do short circuiting. Now how does short circuiting work? There are a couple of different rules how the short circuiting works, but intuitively you can see what happens. When the real node D goes, the real node D should be removed, but also the virtual node D should be removed, right? How do we remove the virtual node D? Because it's connected to a node of another bubble up, up level. So we must find a way to replace this. But now if you see, C is connected to virtual node C, and the virtual node C is connected to B. Now, of course, this is not necessary now, right? Because this virtual node C has lost its real child, say D. So you have C, C, B, D. Instead, what you can do is you can delete C. This is the short circuiting. You can delete virtual C and move virtual C to real D. So the virtual C now takes over the previous D. So now we are fine. We lost one real node, we lost one virtual node by short circuiting, and we changed over the duties of the deleted D to the real C. All right, and now we are back to normal. We still have a balanced binary tree structure. We still have a balance which may look slightly different than before. It doesn't, for example, here it was very A, B, C, D. This whole subtree looks very balanced, but here it's slightly different. It's A, B, then B, C, C, and then so on. But we are back to a good balanced tree structure, and that's basically a high level intuition of how this whole forgiving tree would work, right? Any question here? Okay, now let's really see how this works in a distributed manner. Remember that this is sort of the high level intuition which we are doing on paper and pen, right? So by looking at it, but this all has to be done by the nodes without the knowledge of this tree, right? So as I said, the main thing is how does a virtual node get assigned to a real node? How does a real node know which is its virtual node? And then how does the real network look like? Okay, so not going into a lot of detail, but the main thing, like I said, somehow each real node has to simulate at most one virtual node. But also in the way, like you saw the tree, how it looks like, there's a parent, there are children, and so on. So this is sort of nice. Why? Because what we do is we say that every node, every non-leaf node is going to create a will. Now this will is this balanced binary tree which will replace the deleted node, right? And this will actually have the details of which virtual node you are going to simulate. So the whole idea is you do some preparation in advance. Every node has certain information, which is okay, roughly you can think. So how do I create, if my neighbor is deleted, how do I know I can connect to my neighbor of neighbor? Remember that this is an overlay network, a peer-to-peer network. So if you have the identity or if you have information of somebody far away from you, you just need to request an edge and you will get the edge, right? So the main problem here is how do I know who to make an edge to? Now this is what the will does. So every node, when the system is set up in the beginning, looks at its neighbors and decides if I am gone, these are my neighbors who will replace me by this balanced virtual node. And what does that mean? That means that node creates its will. For example, I create a will, and in that I tell my, say, child A that when I'm gone, you connect with your sibling B and C. So basically, I give A the identities of B and C. Similarly, I give B the identities of C and D. I don't need to give them identity of all the children. Why? Because remember, we are in the congest model. The number of your children could be quite huge. If you tell every child the identity of every other child, it may be much more than a constant number. So you can at most send a constant number in one round, and we want to set this up very quickly. So the good thing is I don't need more than a constant number. I only need a constant number because remember the maximum degree of a virtual node is 3. That means it can only take 3 neighbors. All I need to give it is 3 neighbors. That's all. So basically that's sort of the clever part here. So this wills, which is this balanced binary tree, is given in advance, and then you keep updating these wills as you need. Okay, so hopefully this figure will make it clear. So now if you are node X, you have a parent P, you have children A, B, C, H. Now X is going to create its will. Now what is X's will? So X's will is actually this structure, this balanced binary tree. We call it RT. So RT means reconstruction tree. So the will of X is the reconstruction tree X, okay, which has A, B, C, H, A, B, H, and P, right? This whole structure. And this is the will. Basically, you set up the data structures. So for example, you tell P that your next H parent should be, you tell H your next H parent should be P, and you tell H that the part it needs to know. So for example, P only needs to know this part of the subtree, so it's given this part. A, for example, needs to know both these parts where A and A dash appear, and also this whole subtree where the neighbors appear, right? So on, like C needs to know this part, C and C, and also CB, CH. Okay, and this is basically what you get. Now you can see that each of these parts are quite small, and they're only a constant size. That is, they only need to know a constant other neighbors. So basically, this is what happens. You prepare this in advance, and you send this out. Every node has them. As soon as a node is deleted, this gets executed. That is, the nodes will ask for these edges, they put them in, and then they do a quick update, which will update their will, which is also something you tackle technically. Okay, so I've already explained to you what an air is. Basically, I'm just going to skip this part. I think I've also explained basically what happens if a leaf is deleted. Not going into too much detail. There are a couple of different cases when a leaf is deleted and so on. But basically, this idea was this, like I told you here, that for example, when Z is deleted, Z is already simulating a node up level, but its own parent, like this virtual node Y, now becomes loses 1 degree. So it need not stay, it can just take over Z's position and thus short circuiting. All right, so that's a high level intuition about how forgiving tree is working. Now the other important thing here is what I said about the virtual mapping. So the mapping between the virtual tree and the real network is a homomorphism. Okay, so what is homomorphism? Basically, in this context, it is that if you have these two objects, and these are two graphs, so G1 equal to V1 E1, G2 equal to V2 E2, then every edge, so every edge in the first graph maps to something, which could be another edge in the second graph, right? So there is a mapping which maps every vertex in the edge to another in the second graph. So for example, if you look here, so this A, B, C, D are the real nodes, and A, B, C, the yellow ones, the virtual ones. If you see, the A dash actually maps to A, because in the real graph there are no virtual nodes, so they just map to the one which is simulating them. So the yellow A maps to blue A, yellow C maps to blue C, yellow B maps to blue B. Now you see how does that make the shape of the real graph look like? Very different, because A and A collapses, then you have an edge between A and B. C and C collapses, you actually have an edge between C and D. B and B collapse, which means you have an edge between real A and real B, and real B and real C, right? And similarly, you have an edge between real B and real parent. All right, so that's what's happening. In fact, for example, you look at this mapping, which may be different. You can actually see that the real graph is now not even a tree. So the forgiving tree is a tree, but it's possible that the real graph may not be a tree anymore by the homomorphism. So here, in fact, it has cycles, but we are not bothered about that. Our main purpose is served, and you can easily see now that the degree of the node and its simulating node, so the real degree of the real node plus vertex plus virtual node, is going to be higher in the forgiving tree compared to the real graph. So which means if you guarantee the degree increase in forgiving tree, you guarantee it in the real graph also. It cannot be more than that. Plus, if you see, distances collapse, right? So distances are actually higher in the forgiving tree and lower in the real graph because they're actually collapsing. So again, if you, whatever distance you guarantee is going to be higher in the forgiving tree, it's going to be upper bounded in the forgiving tree compared to the real graph. That's how we get the. So now this is where our virtual graph healing approach guarantees us the results. So if your property A is maintained on the virtual graph, it is also maintained on real graph as soon as you set up the right mapping. Like I said, the mappings here are degree increase is greater in the virtual graph, and distances are also greater. I'm not sure what the arrows I put here are implying, but that's what they are, right? Okay, any questions? Okay, so one more thing, what about if an adversary is allowed to insert nodes? So it's not fully clear how to still run forgiving tree with node insertion. It's still an open question. So, for example, since it's a tree, now the forgiving tree is a tree, so you're going to bring in an edge, so you still need to do something. If you want to keep it as a tree, you can only accept one edge, right, of all the edges coming in. So here the idea is the adversary can bring in a node with any number of edges. So those will of course be added to the real graph, as in a peer-to-peer network. But for the forgiving tree, you can accept at most ones, right? At most one of them. So whichever one you accept, it will still be a tree, but that doesn't solve all the problems. Why? Because you still want to maintain the properties of the forgiving tree consistent with the real network. Remember the diameter. All right. Okay. Sorry. There's one more question here. Why does the forgiving tree maintain the diameter of the real graph? And that is basically because if you construct a spanning tree on the real graph, it basically has the same order of diameter as the real graph, right? It's at most twice. So when you constructed that spanning tree in the beginning and maintained it, in a sense, you were also maintaining the diameter of the real graph, because the diameter of the forgiving tree was at most twice the diameter of the real graph, right? So now that can change here because these nodes are being added later on. So potentially you could decrease the diameter of the real graph, but the way you choose the edges, that may not always reflect that, and potentially there could be some issues which we have not completely figured out yet. So okay, one heuristic would be you connect to the lowest depth tree, lowest depth node to try to shorten the distances, but you may still not be able to guarantee what the relationship between the tree diameter and the graph diameter. Okay, sort of a question. The other thing you could do is you say, okay, why don't I just keep all the edges which came in and instead remove certain edges inside to shorten the distances. Now that's fine, except that now the virtual tree is a problem. Because you have these virtual RTs and everything, you will need some very clever mechanism if you have to delete edges inside the forgiving tree, right? So maybe it's possible, but we haven't figured this out completely yet. So it's sort of open. These are open questions. Plus, there is a very interesting fundamental question which is going to be raised in the next slides, which is also applicable here.
I have a question, Amitabh.
Sure. Yeah.
So removing nodes. There is an echo. I don't know. Well, anyway, so removing a node simulates crash failure, right? So that is kind of natural. Adding a node. So what is that simulated or modeling in reality? Like kind of what I mean, what could be that the situation?
All right. Yeah, of course. So actually, it's in some sense it's important because it's simulating a real peer-to-peer system. So in a real peer-to-peer system, you have nodes coming in and going out all the time, right? So even though that simulates just the crash failures, but it will not simulate sort of a real peer-to-peer system in action, right? So in a real peer-to-peer system, you may have nodes which join, right? So that's sort of the motivation.
I see. So you see that as an adversary, like. I mean, that makes sense because you should react quickly to these changes in the environment. It's not like a bad thing, but it's just right. The system is changing.
But you make a very good point. Actually, the next slides somehow address those. You are right. We are saying at a high level it's an adversary bringing the vertices in with the edges, but in fact we are not paying anything for it. So you have a good point. Yeah, the deletion is actually simulating crash failure, which is actually the more costly thing. But whenever some node joins, it is in fact like free, right? It is still, even though we are saying an adversary is causing it to join, in some sense it's free because it's not really like a failure fault.
But you know, in a system, maybe in a real system, because here the adversary is the idea is that this evil entity will do whatever this is possible to make your life bad. But let's say maybe in a well-designed peer-to-peer system, maybe every time that a node joins the computation, it will not create so many connections. That maybe because that's the part of the protocol, no? That you design the system in that way.
Sure.
So I don't know if that that wouldn't be like the adversary. Right.
Yeah, I mean, so the next paper is actually going to, in some sense, answer this question, hopefully what you're asking. But your intuition is sort of correct. So that is why we are not, we do not charge. So if the adversary brings in the edges, we are not charging the algorithm. So if the adversary likes to bring in 1,000 edges, connects everybody, it's not our problem, right? So it's not the algorithm's problem. So the algorithm is not charged if the adversary brings in edges.
Okay.
I think it's sensible, right? How can you charge the algorithm for somebody coming in with a lot of edges, right? Okay. And maybe they come in with low edges, that's also fine. We are not charging either way. Okay. So yeah, hopefully the next few slides is actually going to address the same question. I think it's a very timely question.
Okay.
Right, great. Thanks for the nice question. So now we'll look at an extension of forgiving tree, which is the forgiving graph. So this was a paper, the forgiving graph, a distributed data structure for low stretch under adversarial attack, which was in PODC 2009 and distributed computing 2012. All right. So now basically we have looked at dash and forgiving tree. And yeah, hopefully you notice that dash was not using virtual nodes. Forgiving tree was. Now, forgiving graph is an extension which tackles stretch, which is actually a much stronger property than diameter, because stretch basically says consider any two nodes in one graph and then look at another graph after say many steps, and again look at their distances between them. So every pair of nodes, and if their distance has increased, by how much has it increased, and then you look at the worst increase. So it's possible the diameter has stayed same, but two nodes have gone very far off from each other. We don't want that to happen. That's the first thing it looks at, but it looks at something even more important possibly. So coming to that is that it's a fully dynamic system. That is, it handles both insertions and deletions. So this is basically similar. This will, all the questions Armando was asking come here. So like I said, it bounds the stronger property of stretch, and it is more complex and a bit slower than the forgiving tree because of all of these things it allows us. All right. The first fundamental question to address, however, is how do I analyze the self-healing algorithm? How do I analyze forgiving graph or a self-healing algorithm which permits insertions? So does anybody see a problem here? In other terms, the question is, what does G0 look like? So remember, I can now insert vertices, insert nodes. So what is the smallest possible G0? And now if you think about it, how did my results in forgiving tree look like? So my results in forgiving tree look like at time t, the degree of node V in GT is the degree of node V in G0 plus 3 at the most, right? Or it looks like the diameter of GT is at most log D times the diameter in G0. Right? Now, what can G0 look like in a forgiving graph? It can in fact be empty, right? Because remember that insertions are happening So we could have begun with an empty graph and we'll still be with a real graph by the end, right? Or real network by the end. So now it's a problem. I can't really say that my diameter at GT is log D times G0 because it's 0. So I can't, that's no guarantee that, my diameter is at most 0. That'll be absurd, right? And if a node V did not exist at G0, I could possibly say its degree is 0 plus 3, but that may not be accurate also, right? I mean, if I say degree of a non-existing node is 0, which is another not clear thing to say, right? So it's sort of tricky. But instead, what we do is we use something basically which follows from our discussion 5 minutes ago about insertions being a different quality, being a different thing than failures. So in some sense, I think what Armando said brings this to fore, that deletions are like crash failures, which are like really harmful, but insertions are what the adversary is bringing in. So it's not something under our control. And it's in that sense not really that harmful, except we have to handle, the algorithm has to handle those insertions if they are causing any issues, right? So sort of thinking on that notion, we also came up with this idea that now we maintain 2 different graphs. The first one is the graph of only insertions and original nodes, which are already there. And the second is the actual network at the present time, so the healed network. So the one on the right side is the healed network, the one on the left is the node of only graph only insertion and original nodes. So, and we maintain both of these, and this is how we give our results. So we say, for example, this distributed algorithm is an algorithm such that the stretch, that is the distance between any 2 nodes in G, present G, is less than or equal to log n times the distance in G dash. So we are maintaining both the graphs, but the graph on the left does not have any deletions. So we do not have any deletions happening in the left one. The right one has deletions and healed edges. Okay, so it's sort of preserving how the graph would have looked like if there was no crash failures or no attacks of the deletion kind, and the right side is what is happening really now. So with deletions, okay, and then we can sort of compare both of them, and then the guarantees basically become similar, that now we bound the stretch to at most log n. So as you see, stretch is more difficult to guarantee. Is that sort of does that sort of make sense? Now similar with degree increase. So degree increase now is higher in forgiving graph than forgiving tree. Instead of being plus 3, it can be 3 times. So the degree can be at most 3 times the degree in G dash. So for example, if degree of UV was all right, so the figures are slightly messed up. So this here says the degree of node V in G dash is 3 and degree of node G in V is 5. And the distance here is between U and V is 3 and distance here between U and V is 5. So the figures and the results are mixed up, but you get the idea, right? So this is a choice we made, and sort of the reasoning for those choices sort of is hopefully clear from the discussion previously. Maybe there are other ways to present the results, we're not sure, but this is what we did and what was, let's say, accepted by the community, at least for these papers. Okay, so that's sort of our main result. So the degree of node in G is at most 3 times degree in G dash. Distance between any 2 nodes is at most log n times the distance in G dash. Now this is also has a matching lower bound like it was with forgiving tree, and I'll present the bound, and I think the similar one carries over. The cost, now the repair of the node of degree D requires at most order D log n messages of length order log square n and time order D order log D log n. So everything is slightly more difficult here because for a fully dynamic system and the costs are a bit more higher. The time is slightly more higher than the forgiving tree, but all of this allows us a lot of flexibility, right? Any questions? All right, so first sort of like look at the lower bound, because it's quite easy to see once you have the idea and you can fix it. All right, so like what we're trying to say is that the stretch, the distance between any two nodes. Let's look at the graph GT and G dash T is at most log n times their distance in G dash T. So this is how it blows up. But now imagine what you can do when this red node is being deleted. What possibly can you do? Okay, that will give us the lower bound. So if you have a node, here, the red node, imagine it is the center of a star, right? Every node is actually center of its own star, right? So what can you do? So you can take the neighbors and put in some other structure, okay? And now that structure will basically, whatever structure you put in, which maintains connectivity, right? Technically, has certain properties. So it will, in some sense, what we saw, it will either maintain the degree, reduce the degree, or reduce the distances between nodes. We saw the differing strategies, right? But whatever structure you put in, you can, for example, let's look here when X is deleted, and let's concentrate on two children or two neighbors of X called Y and Z, right? Now, see notice the difference here. When we come to forgiving graph, since we are looking at a fully dynamic system and where we don't have a tree structure, we don't have any parent-child relationship now. We don't have a spanning tree or a directed spanning tree, whatever. We don't have that. We just have a regular graph and neighborhoods, right? So all of these are now neighbors of X. Now, assume that whatever structure is put in place of X to get back connectivity, look at two nodes Y and Z. Y and Z in this, and you can now imagine in that structure you can create Y as, you can take Y and do a breadth first search from Y into that structure, right? So now you create sort of a breadth first search tree of that healing structure which you have put in. Okay, now when you do that, what will you get? Either the structure is quite shallow, which means there are some nodes which have quite high degree, right? This repair degree, or it is narrow, or it is sort of tall. Now, what does that mean? That there must be sort of low degree as you go along, right? So either way, let us say that you limit the degree increase. So you say the degree increase is at most alpha, right? So that's what you're trying to limit. If you limit the degree increase to alpha and you have n neighbors, this means that you must give a stretch of, you must blow up the distance between Z and Y, assuming this Z is on one is a leaf node. So you take a node Z which will become a leaf node if you do a breadth first search tree traversal, and you take Y which will become the root. Okay. Now if you limit the degree increase to alpha, that means the maximum degree you can have as you grow up is basically alpha minus 1. So as you grow up, you're limiting your degree increase. So here is alpha minus 1. Here at the Y, it's at most alpha because Y was a leaf node, and now it had just degree 1, or maybe this should be alpha plus 1. I don't, it's exactly what should be. So now if you see, you must have your at the most, since at the most there are alpha vertices a node can have, you must have a path of log alpha n going up. right? So you are only getting at the most, removing at most alpha nodes on the way. So you have to blow up the distance between Z and Y by, so here the distance was say 2, right? Now here it is some factor of log alpha n minus 1, right? So that's sort of the lower bound. It basically comes from the trade-off between degree and distance on a DFS tree, right? Is that clear? So just, there are of course factors of 2 here, or more 2 times, or 2, but it's all in the constant. So that's basically why this always has to happen. Okay, any questions? All right, so now if that gives us an idea that if you limit the degree to a certain constant factor increase, you will have to do a log of that, log of base of that as the stretch on a graph. And a similar lower bound, similar technique applies to the forgiving tree, which I didn't discuss, where you just talk about the diameter, but I mean diameter is simply also a stretch, like a verse stretch in some case. So that's how both are in some sense similar. Okay. So now let's move on to the real forgiving graph algorithm. So firstly, there is node inserted. There's no restriction, come with any number of edges, whatever. When a node is deleted, now we are going to introduce a very interesting structure which I really like here, called a half full tree. And we're going to, instead of the balanced binary tree which we rooted there, it's a very similar structure, but it has some sort of properties which are quite useful here. The important thing is, what we need from this half full tree is, then if 2 half full tree become neighbors, we must merge them. All right. Now, why can stretch increase? So why can stretch increase, for example, in the even in the forgiving tree? I mean, firstly, as soon as you create a tree, look at a cycle, for example, you remove one edge from the cycle, the stretch has already blown up by the diameter, right? By n. Why? Because you have 2 neighbors here. Now this edge in the middle is gone, so you have to go all the way around to reach this node. So previously the distance was 1, now it's n, right? N minus 1. So that is why forgiving tree is already bad for stretch. As soon as you create a spanning tree, you have a stretch, possible stretch of n, right? So that doesn't work. And as soon as you use any spanning tree. So here also you have to be careful of that. So what you always need to do is, when you have these structures which are coming up, you need to somehow merge them. So you need a structure which should be nice to merge. So that's what you're going to do. As soon as 2 half full trees become neighbor, you merge them to create another one which brings the nodes together. And the same idea of virtual nodes is actually going to be used from forgiving tree into forgiving graph. All right, so this is similar to previous. So you're going to now replace V by hello, can you hear me?
Yes, I can hear you.
Oh, okay. I got a message that my connection was going bad. All right. So what do? So you take V and you replace it by a reconstruction tree of virtual nodes and real neighbors of the leaves of the tree. So this is similar to what we had before. Now the new thing which happens is merging of 2 reconstruction trees, like I said. So if you have this X which has 2 of these ovals as neighbors, it's going to somehow merge them together, so that like LMNO over these real leaves, PQR over the real leaf, they'll now merge together into LMNO PQR and create a new one. So this thing needs to happen. Now that's of course easier said than done. Where is this? Okay, so this is the same as similar to forgiving tree. Virtual node has degree at most 3 as internal node. Now the one difference is that because it was forgiving tree, you had one real node was simulating exactly 1 virtual node. And why it could do that? Now if you think intuitively, because it was only going to do the duty for its parent, right? And in a directed tree, every node has only one parent, right? Every node has one parent, so it's only going to do it once, and so it's just +3. Now here this doesn't apply, so you may actually do duty for every neighbor. So every one of your neighbors may be deleted. So you may have to create a virtual node for every one of your neighbors, That is why your degree blow up can now be 3 times your degree. All right, so that's a high level intuition. Instead of +3, it will be 3 times because you may have to simulate for every neighbor. All right, and now the distance between two nodes, like we are maintaining now stretch, can only increase by factor of the longest path in the largest RT. Remember now what we are doing? We are merging the reconstruction trees. Now potentially that means you could have order n nodes in a reconstruction tree, because you could have brought in many nodes from the neighborhood and brought them together. Now this could be n by 2. Of course, you have lost a few nodes, so it's not exactly n. It could be n by 2, or actually you have, whatever. So you could have potentially order n of them. So the guarantee now becomes log n instead of log d for diameter in the forgiving tree, right? Because that's the maximum distance. All right, now to the most sort of nicest thing I think we had in this paper. If you are still awake and active, you may want to pay attention here, because this is I find it a beautiful data structure, which we like to think we invented, but surely it must be there in somewhere. So the idea here is that you have a kind of a balanced binary tree, but with these special properties. We call this half full tree. So a half full tree is a rooted binary tree. So it's a binary tree, but here every non-leaf node, so looking at the definition, every non-leaf node V has the following two properties. So V has firstly exactly 2 children, and the left child of V is the root of a complete binary subtree containing at least half of V's children. So let us look at this property a little bit carefully. So for example, if you look at the red node on the top, it has 2 children, the green one and another red one. The green one, like we said, the left one is always a complete binary subtree. So this is a complete binary subtree, T1, and it has at least half of V's children. So what are V's children? So V's children are this node plus T2 plus TK, all of these things. But if you think about it, the binary tree has a binary 2 to power some number of children, and if T2 and all of these are smaller than T1, and the same property applies, then T1 has a sum. The sum of children is greater in T1 or equal to what these are here if exactly these properties apply, right? So okay, hopefully this definition will make it even more clear as you go along. Now this can be applied to everyone as okay. For example, let's look at the green one. Now the green one is heading a complete binary subtree. So it's a full binary subtree. Now look at the left child of the green one. Look at the left child of a green one. Now it's a subtree of a complete binary tree, right? So it is also complete. Now you look at its right child. Now that is also heading a complete subtree. It's also complete, and moreover they are both of the same size. So in fact a complete binary subtree itself is also a half full tree, right? So we said at least half of V's children. Now this creates some very interesting properties. Firstly, let us look at the first 7 of these half trees, which I call the 7 summarize. So now if you look at this is how they look. In fact they are fixed. Their shape is exactly fixed. There's exactly one. So you have just a single one. You have this complete binary subtree of 2 leaves, which looks exactly like this. You have one of 3 leaves. Now 3 leaves, if you look at the top, the left child has a complete subtree with 2 leaves on 2 leaves, and the right one is also a complete binary subtree, in fact, of just 1. Now this is with 4 leaves. As you can see, when it's hitting this power of 2 numbers, is actually a complete subtree itself, a complete binary subtree, a complete binary tree. Now 5 leaves. Now again you can see the same property here. If you can verify it if you like. Now you have 6. Now you have 7, and moreover they are exactly like this. You cannot have anything else here, right? So now this creates some sort of nice properties. and let us look at these as we go on. Now, in fact, you can even just make a binary representation of these, of the leaves, and you will get some intuition about how the trees look like. How is that? Write this half full tree, the number of leaves of the half full tree in binary. So let I be an integer, and there is a unique half full tree T which has I leaves. So for example, if you look at 6 leaves, now how does that look like? 0, 1, 1, 0. So let H be the number of ones in the binary representation of I. Then T has H minus 1 spine nodes and H primary roots. Okay, let me show this terminology by figure. Seems like, okay, there's one figure here. Okay, now, so what got missed here, and I saw that should have mentioned it, is slight terminology here. So the red nodes, okay, let's come here. So if you look at this figure again, what does it look like? So if you look at this figure again, what does it look? It looks like these red nodes are basically forming. They seem to be like like a clothesline. So think of a clothesline where you're putting clothes. So this is like the red nodes are like a clothesline, and the trees hanging below them are like clothes you have put out to dry. And imagine that you're always putting the heaviest clothes on the left and towards the lighter clothes on the right? So you begin with your heavy winter jackets, which is the T1 on the left, then the lighter jackets and shirts and so on, shorts in this order, right? So the red nodes are what we call as the spine nodes because they look like a spine, right? And the green nodes are what we call as here primary roots. So the green nodes are the primary roots. Why? Because they're heading a complete subtree. So that's sort of the idea. And now you can look at the binary representation and it makes sense. So if H is the number of ones in the binary representation of I, then there are H minus 1 spine nodes. So now if you look here, there are 2 ones, but there is exactly 1 spine nodes and there are H primary roots. So there are 2 primary roots, right? And moreover, if you look carefully, the first one is in the 2's position and you have a complete binary tree of 2 leaves. And the third one, the second one is at the 4's position, that is at the 3 position. So, okay, this is 2 to the power 1, 2, and this is 2 to the power 2, 4, right? So this one is representing a complete binary tree of 4 leaves. This one is representing a complete binary tree of 2 leaves, right? Subtree. So just by looking at the binary representation, you can actually get quite a clear idea of how the tree is. Now, why is that helpful? Because you can actually do some binary maths, and that binary math sort of is analogous to doing a merge. So what you can do is you can firstly do a strip. The strip will remove the spine nodes till you're left with complete nodes. Now you join the adjacent trees with the new node as the root and larger tree as the left child. So this is the advantage of working in the virtual space now very clearly. Why? Because these are virtual nodes, you can easily delete them whenever you like, and you can easily reinsert them whenever you like. You can create new ones, remove old ones. So this is what we're going to do. When we do strip, we just remove the spine nodes, which are again virtual nodes, and then we again merge them, and always we keep the bigger trees to the left and get a new one. So for example, here you have 0, 1, 0, 1, this is the 1 on 5, plus 0, 0, 0, 1, 0, plus 0, 0, 1, which is a single one. Now here you're going to remove this top vertex here. So you will be left with 2 nodes which are singletons, 1 complete binary tree with 2 and 1 complete binary tree with 4. And then you basically just merge the shortest ones always together. So you'll take these the 2 singletons, and you'll get this a complete tree of 2 vertices on the rightmost side Then you'll take these two, you combine them with the virtual node with another virtual node, and finally you'll combine them all with another virtual node on the top. And now you can see you're left with 100, 000, 000. Now this is actually exactly like the binary addition on this. So if you do a binary addition on these numbers, which is actually not surprising because this is 5 plus 2 plus 1, 7, 8, which will give you the same in binary. And you can in fact see that the number of ones here is 1. You have no spine nodes, and you have one. You just have this one as primary root, right? Does that make sense? So that is why we sort of like this structure. Let us look at this in action, and you will also see why this structure actually is useful in practice. So now also you can compare how the forgiving graph works with the forgiving tree. So now here if you have a node V which is deleted, so node V is deleted here. See, there is an edge called XV. You can also look at this edge called XY just for understanding. So now here, all of the neighbors of V contribute a virtual node. So U contributes U dash. X contributes X dash. W contributes W dash. But T does not actually contribute. So you don't need all of them. You need just one less because it's just another binary tree here. You don't have the air. Now you replace it by RTV. Now node Y is deleted. For example, now X is going to contribute X double dash and Z dash. Z is going to contribute, say Z dash, right? Now you can see what's happening. X is now adjacent to both of these RTs. Node W is deleted. So when W is deleted, it has an edge inside W dash, inside this one, and it has an edge inside this. So now this is going to cause a collapse because we need at least some contribution from one of these. So instead what's going to happen is it's going to initiate a merge. It's going to cause all of these to merge together. And now we have a merge where X is contributing X dash, X is contributing X double dash, U is contributing U dash and U double dash, and Z is contributing Z dash. So all of this merge, RTV, RTW, and U, they all merge together. Right? You see it's a more complicated structure than forgiving tree. All right. So the question is, where is the half full tree? The half full tree disappeared because it was a virtual structure. It doesn't look like a half full tree anymore. It looks sort of strange, complex. So this is where again our old friend, the homomorphism, comes. So virtual half full tree and its homomorphic image could now be more complicated than the previous one. But this is basically somehow another way to visualize this, maybe like this. So now you may want to visualize these as there's another level of visualization here, which is this virtual structure, and another virtual structure which is like the half full, looks more like the half full tree. But here you then may have to basically imagine all of the edges separately. So ZX, X, XY, you create another more copies of X in some ways just for understanding. The real structure is of course on the left, but if you wanted to imagine how it looks like as a tree, you can imagine in this manner, right? And that's basically what you get. Okay. Any questions? All right. So ultimately, then let's look at a quick couple of more technical things to give you an idea. So then this is a distributed algorithm, which, like I said, blows up degree at most 3, distance is at most log n time. Repair takes so much cost messages, and let's very quickly look at the results. So stretch at most log n times the distance in G dash T, and this we now already know. Why? Because you can combine get all of the log n within that, which is at most log n the distances are at most log n between in a tree of n leaves. The distance is at most log n, right, between two nodes. And if the original distance here is 2, this can basically follow from that. I'll sort of not bother about that now. The degree increase is actually slightly more complicated because now you have to prove that each node has at most one helper node per neighbor. This we already know that an internal node of a binary tree has degree at most 3. So if we can prove that every node has at most one virtual node per neighbor, then we are fine. And basically that means that each edge, so imagine that this is an edge, Vx is this edge, that each edge contributes at most one corresponding helper node, then we are done. So there are some small number of cases here, but the idea here is for example, this Vx is going to contribute V dash in the tree. Oh, this is the figure. I want to have this information there also. Okay, the distributed, how this is set up. Okay, so this gives an idea of what should happen. Once you prove that, that's fine. Let's look quickly at this quite interesting idea. Again, we'll not go into detail. Now, how does this merge happen? When we are merging, how do we achieve this merge such that we can always find this pair kind of nodes here? Okay. So what we do here is that we define something called a representative. Now, representative is defined in this manner, but not going into all the details. Basically, the idea is similar to what we had in the forgiving tree with the air. And that idea is you always have one node, one leaf node, which is pair, right? Okay, so the question basically what I'm trying to solve here is, remember when we did the merges, we had this tree on the left and this tree on the right, and we created a virtual node. Now this virtual node is going to be created, that's fine. But remember, every virtual node which is created here must have some real node simulating it, right? How do you know, how does the real node know I am the one to simulate this new virtual node? And how do I know how to create this virtual node? So that is this mechanism which we call as the representative mechanism. At a high level, the intuition is simply this, and then it's sort of easy to follow without getting into too much technical detail. The intuition is simply this: whenever you have this binary tree, balanced binary tree, you always have one node which is pair, like in the forgiving tree. So for example, when you have A, B, C, D, so you have this tree which is A dash, B dash, C dash. Now this D is not doing anything. So if B dash on the top can remember that D is the guy who has pair capacity, and that it calls its representative. So it's going to call D as its representative. It's going to remember that. Similarly, here is another one which is A and Z, and it's another vertex, virtual vertex A double dash. It's going to remember Z as its representative. So then what you do is when you merge both of them, you are just going to merge these. So A dash, B dash, C dash, A double dash, and the root of the larger tree becomes the virtual. The representative of the larger tree becomes the virtual node, which becomes now D dash. Now D dash will then inherit Z as its representative. All right. So that's sort of the idea. When they come together, they talk to each other. They say, my representative is this, your representative is this. I am the bigger tree. I will create a virtual node, but I'll take your representative as my new representative. So that's how you keep the information. The whole idea here is how to maintain the information without losing it when all of this is happening. That's the basic idea. And then simply that, you just keep doing these things. Similarly, when you split, now the other thing is when you split, again you have to get the right information. So this is the same thing happening here. Now these trees are actually breaking up, but when they break up, they still keep the right information. Not going into detail, but you can, it's a cute way you can keep doing this. Okay, so okay, I will skip the proof now at the moment about helper nodes, but basically comes from this case analysis that you can always do that. I think that's a little bit longer at this time, so we'll just skip that. So this is, we are still not fully done because this still doesn't show us completely how to fix it. So there's more detail in the paper. But now the basic idea is you still have to put in a temporary structure as soon as this breakdown happens, as soon as a node is deleted. Again, remember, when insertions happen, nothing to worry about. When a deletion happens, crash failure happens, you can't immediately do merging and everything. You still need something else. But what you do instead is you create a binary tree, like a scaffolding structure. So you create a temporary connection between all of the neighbors, like another binary tree, and then you use that to detect, like the question the nodes ask is, am I a primary tree? If I'm not, who is my primary tree? Find the primary root, sorry. And from there you initiate merge by using the representative mechanism, and you go up that tree and you create a single helpful tree. So there are a few details in the technical part of actually how to implement this in a distributed manner, right? So any questions here? So this sort of storage is slightly more complex, but now stepping back, what is the general strategy for self-healing so far? For at least these topological things has been the following. It's a local process, but you maintain global invariant, so you need some structures which you put in. For forgiving tree, a balanced binary search tree was enough. For a forgiving graph, you use a half full tree. For X-heal plus, which we are not discussing, you put these things called k-regular expanders. For DEX, which is deterministic expander, which is just the thing that you put in a deterministic expander. I'm not going to go, if you know, it's fine, but moment it's difficult to sort of explain right now. So you put in another deterministic expander. The idea is you can maintain these properties as you over all the series of attacks. So basically that's the idea so far, and it'll be great if you guys can propose your own problems and feel free to discuss with me whatever and see what problems you may want to solve and possibly structures to put in. That's sort of what is working here. Now very quickly I want to mention this idea of functional self-healing, where you have some process and you want to, so while you see the previous works were maintaining sort of this architecture, this topology. Now if you have things happening, what can be done on this? So there are some papers on this where people have tried to look at functional self-healing things, trying to maintain things while the structure is changing. I have this couple of papers actually with Armando here, so he's also an expert on this. So now what we want to do here is this very interesting field of compact routing. Again, if you know this is nice, is fine, is good. Not go into a lot of detail, but basically the idea is you have routing, which is basically sending messages from one node to another in a network. But you could possibly have failures during the routing. So a messenger may have an accident, and for example, if the queen is sending a message to this place, which was actually center of Loughborough, now you can think of center of Durham, but the car which is going may fall into a ditch, you may lose the message with it, right? So you want to avoid that. So the question is, how do you route this message from sender U to V despite failures in the network? But we need to give something back. So we're going to say, despite failures, node failures in the network, but the network is now reconfigurable over the networks, but the nodes have low memory, right? So those are the sort of constraint. Why about low memory? Because in particular, compact routing is a field which tries to always say, how can we have all of this routing where nodes use very little memory? So it doesn't make sense to be having high memory, because then you can do regular routing So we want to have self-healing, which is in low memory. So that is why we came up with new models, which I'm not going to discuss right now. We call it compact local streaming, which limits the memory on every node. But okay, the high-level idea is you have a compact routing scheme. There are a few which works without any failures. And now basically what that has is either it has a packet header which tells the destination and the sender and the information you need to send on the way. And now the idea is you have one scheme S which works without failures, but now you also have these failures happening, so you have to bring in a self-healing structure. Now this self-healing structure, which we have been calling reconstruction trees for now because they were always trees, but they need not be trees, they can be any structure. So let us call it RS. Let's call it a reconstruction structure, RS. Now this reconstruction structure should also have its own routing scheme. So basically, when you put this virtual structure, if the message has been coming, is there a nice way so that it goes out to the right place where it should have gone if there was no failure? Then that scheme is, let's say, R. And then basically, if you can get these two things together, these three things together, then you can basically integrate S and R transparently, and you will get this kind of scheme. So now you can sort of think that if a message is going from V to U, the green ones are the original scheme, and these other colors are the S, the scheme which come with the self-healing within the self-healing oval, and they go all down. Now in our work, we were luckily able to devise these schemes. So the compact reading scheme which we looked at is called the Thoropzwig's routing scheme, and this is over trees. So we only looked at the forgiving tree or the tree kind of ideas at the moment. The others are still open or partly solved. Now we still have to tackle how do we do self-healing with low memory, which is a challenge. So we do the self-healing with low memory, and so you devise a forgiving tree, but which was working in low memory. Now the nice thing about the tree which we put in, now if you think about it, if you put a balanced binary tree and you label the leaves such that they are in an order, right? So if you put in a binary search tree is basically what I'm saying. If you put in a binary search tree, now if you think about it, you have a free routing scheme, right? How? Because if you have to send a message to say node 5 and the nodes are arranged in a order, so say they are 1, 2, 3, 4, 5, 6, 7, 8, and the tree inside is also in a search tree manner, that is all the nodes to your left are smaller, all the nodes to your right are larger, then you have a routing scheme, right? What is that routing scheme? You simply go, you look at, when you come to a node, you look if the message you are sending is smaller, is being sent to a smaller vertex, you go to the left. Being sent to a larger vertex, go to the right. You reach the right place. So it's essentially almost free. So you have that S, so you have R, you have S, and then you can get S plus R if you integrate them both together. That's what we did. And this is what we came up with, a scheme which goes on. And then in this work, the pre-processing was in regular memory. That is, we couldn't do it in short memory. But in the other paper, the second paper, we even managed to do that in short memory. So then we have a full solution. So that's basically it. So this gave us a scheme with sort of a functional self-healing, which uses order log square n memory despite no deletions. And you can deliver a packet if the destination has not been deleted. If it's been deleted, you can still get a message that it's been deleted, and you pay for some extra self-healing latency, which is basically the size of these trees you put in, log delta. So you pay a little bit extra time to reach, but it works. So, right, that's basically it. So in summary, these are some efficient distributed algorithms for self-healing topological properties, and you have a choice of algorithms for different requirements, different resources. And hopefully it's a fast growing area, and you can use virtual graphs as approach, which itself can be very handy. So what in the future? There's many things, many directions which can be done. There can be many empirical studies which can be done. You have many model assumptions which we made. Even the case of multiple failures, we can, if you want to look at, model it, have some assumptions and things which is useful. You can do, for example, these sporadic failures in different parts are actually quite common in high performance computing. So this is where our assumptions are actually quite fine. You are unlikely to have multiple nodes go down in the same neighborhood, so accidental failures. But if you do have these multiple nodes going down in similar vicinity, you may have this an extension you may want to think of. Cascading failures, things going down quickly one after another, high churn. There's so many different things to look at. So what is the best way to analyze this fully node dynamic algorithm? Like I said, we had a particular approach, maybe there are others. Load balance self-healing is something which has not been studied in detail. What if you, potentially our load balance, but if there are others in which you need to worry about keeping communication low between every node, multiple failures, sensor networks, behavioral self-healing, can other theories be applied and taken other places, and kind of others theories and general theories of dynamicity, right? So thanks a lot. This is the traditional unforgiving tree slide which I use. So where you can take an apple, but the tree takes you back. So if there are any questions, I'm happy to answer.
Thank you very much.
Thank you very much, Amitabh.
Welcome.
Very interesting and complete, comprehensive tutorial. Unfortunately, we might have time for just a very short question, but we don't have much time actually. There is a next session that is coming in a minute.
Sure.
Anyway, thank you very much. And if anyone wants to talk to Amitabh to any of these topics, very interesting. So feel free. I guess it's fine that anyone can send you an email.
Yes, of course.
Conversation, right?
Yes. My email is amitabh.trehan@durham.ac.uk, or just Google.
Yeah. No, in the program they might find, people might find your information.
Oh,
yeah,
that's so great.
Yeah, thank you very much, Amitabh. It was very interesting.
Thank you, and see you soon.
Yeah, thanks.
Thank you. Bye.
Bye.
Are we done now?
Yes. So I don't know if the
streaming has stopped.
The streaming is done. Yeah, people is saying thank you for your tutorial.